During this initial reporting period for 1964, major portions of the Manned Spacecraft Center were completed at Clear Lake, some 20 miles southeast of Houston. On February 20th, the first of several mass moves began the transfer of personnel and equipment from 15 leased facilities in the Houston area. By June 30th, the end of the reporting period, the moves were essentially complete, with over 3,000 personnel relocated at the Clear Lake site. Concurrent with personnel moves, major equipment areas were being implemented. In the operations wing of the Manned Spaceflight Control Center, the UNIVAC communication and simulation computers were in operation, and 3 of the 4 IBM 7094 real-time computers had been delivered. Construction in the 2 identical mission control rooms was nearing completion. Installation of control, communications, and display equipment remained to be accomplished. In April, heavy construction was still evident in several areas of the site. Work on the flight acceleration facility concentrated on completing the high acceleration centrifuge. One feature of the operational centrifuge will be an interchangeable gondola system which will permit a payload to undergo testing while others are being prepared. By June, the 10,000 horsepower centrifuge motor was being emplaced. It will drive the gondola at speeds imposing up to 30 times the force of gravity. Construction of the Space Environment Simulation Lab was proceeding on schedule. Steel erection on Chamber A was completed in April. The chamber is 120 feet high and will accept Apollo-sized spacecraft for testing under environments approximating those of outer space. Chamber B will be used for training flight crews and developing environmental control and survival systems. Both chambers will be capable of producing a vacuum equivalent to that found about 75 miles above the Earth's surface. In the flight simulation building, prefabricated exposed aggregate facing panels were being erected. The building will house spacecraft simulation and mock-up equipment for flight crew training. The consolidation of personnel and equipment at Clear Lake enabled the center's research staffs to concentrate fully on manned mission support. Throughout the center, engineering, development, and support skills were applied to such tasks as flight equipment testing. Vibration studies were conducted on the Apollo Boilerplate 22 service module to determine resonant frequencies, mode shapes, and damping characteristics. The results of the tests will help to analyze data acquired during actual flight test. An air-supported vehicle was designed and built at the Manned Spacecraft Center for testing 1/2 scale Apollo docking hardware designs. The vehicle simulates the yaw freedom that will be encountered in docking maneuvers. It is aiding the study of contact and post-contact link behavior. Investigations into the use of an overhead window for the Lunar Excursion Module made possible the elimination of the module's front docking ring. This will result in a weight-saving and simplified operation, both while on and during ascent from the lunar surface. Development efforts on a water-cooled spacesuit undergarment were demonstrated during the reporting period. A small battery-powered pump circulates cool water through 240 feet of tiny plastic tubing sewn into the garment. The tubes are in contact with the skin and regulate its temperature through direct heat transfer. Tests showed that the garment is more efficient, more compact, and requires less power than forced air systems presently used for spacesuit cooling. A number of Gemini spacesuit studies were conducted, including mechanical dexterity and mobility checks, and mobility interface tests of the suit in the Apollo Command Module. The Gemini suit will be used on early manned Earth orbital Apollo flights. This will allow more time to perfect the Apollo suit for later lunar missions. At Wright-Patterson Air Force Base, spacesuit performance was observed under zero gravity conditions aboard a KC-135 aircraft flying parabolic trajectories. A full-scale Gemini cabin mock-up was used in the tests. The successful use of a full-scale maneuverable parasail was demonstrated over Galveston Bay in late May. Radio control was used to steer the parasail and an unmanned Gemini boilerplate spacecraft to a predetermined landing point. The parasail system is being developed for possible Gemini recovery application. Parasail tests were also conducted at Fort Hood, Texas, using a 1/3 scale model of the Gemini spacecraft. The model was carried aloft by helicopter and released at 10,000 feet. A television picture, relayed from a camera mounted in the vehicle's nose, will help instruct astronauts in parasail steering techniques. Radio control is used to maneuver the test vehicle to a predetermined landing point. Techniques for water recovery of the Gemini spacecraft were studied, and tests to determine the best methods of astronaut egress from the Gemini spacecraft were conducted in a test tank and on the open sea. Prototype flotation devices for Gemini astronauts were designed, tested, and evaluated. Both undersuit air bladders and more conventional life preserver designs are under consideration. Speed and the necessity to maneuver precisely and quickly are sensations and functions familiar to both astronaut and race driver. In each case, similar physical and mental reactions are involved. To determine the physiological effects of these stresses, Daytona Speedway drivers were instrumented to record their heart action, respiration, and temperature. Telemetry equipment was placed next to the drivers. While the drivers maneuvered the course, an electronics team monitored their bodily functions. The results are presently under study. On February 3rd, the Gemini and Apollo Flight Crew Office received 14 new members. This brought the total number of astronauts to 29. Formal classroom instruction for the new astronauts lasted through mid-June and included science and technology courses basic to their new spaceflight profession. Geology classroom instruction was supplemented by field trips to areas where volcanic and impact geological phenomenon could be observed. The trips were designed to equip the astronauts with the knowledge needed to conduct basic investigations of the lunar surface and to select the most meaningful samples of lunar composition. The samples will aid in determining the origin of the moon and the Earth-Moon system. The new astronauts were taken to the rainforests of Panama for 3 days of jungle survival training. The instruction is part of contingency training intended to acquaint the astronauts with basic survival techniques should their spacecraft be forced down in inhospitable terrain. In addition to helicopter training to familiarize them with the sensations of flight in the Lunar Excursion Module, astronauts are required to maintain flight readiness in high-performance aircraft such as the T-38 supersonic jet trainer. The first of 15 T-38 aircraft was received by the Flight Crew Office. The trainers will replace F-102 and T-33 aircraft presently being used. On April 13th, a press conference was held at the Manned Spacecraft Center to announce the selection of crews for the first manned Gemini flight. Virgil Grissom was named command pilot of the prime crew, and John Young was named co-pilot. Command pilot for the backup team will be Walter Schirra. Thomas Stafford will be co-pilot for the backup team. The first half of 1964 recorded a number of significant accomplishments in bringing the Gemini program closer to its operational goals. On January 21st, the sequenced compatibility firing of Gemini Launch Vehicle number 1 took place at Cape Kennedy. The vehicle's two stages were mounted in a side-by-side configuration and were fired in series, each for a duration of 30 seconds. The vehicle's successful performance signaled its readiness for the launch of the first Gemini spacecraft. On March 5th, spacecraft number 1 was hoisted in the gantry on Launch Complex 19. The unmanned spacecraft was to be inserted into a low Earth orbit and would not be recovered. Primary objectives of the flight were to test the compatibility of the launch vehicle and spacecraft, and to demonstrate the ability of the launch vehicle to place the spacecraft into a prescribed orbit. In the gantry white room, pre-mating inspections and preparations were undertaken. The spacecraft was then lowered to Gemini launch vehicle number 1, and the two were joined. Launch occurred on April 8th. All test objectives were met. The launch vehicle and spacecraft systems performed within the tolerances required for manned flight. Succeeding Gemini spacecraft were in various stages of completion at the McDonnell plant in St. Louis. Cabin sections in final assembly and checkout included those of spacecraft 2, 3, 3A, and 4. Spacecraft 3A will be a static test article. Its systems will be updated to duplicate those of each flight-readied spacecraft. Its responses to simulated missions in an environmental test chamber will anticipate actual flight article performance. 12 flight spacecraft are being delivered under the McDonnell contract. Spacecraft 5 through 9 were in the early stages of fabrication. Spacecraft 2 was at the most advanced stage of completion. By June 30th, it had completed individual systems tests and was entering the integrated testing phase. Spacecraft 2 is being readied for the second Gemini Titan or GT2 flight. It will be an unmanned suborbital mission scheduled for launch in the fall of 1964. The test will emphasize qualification of the heat protection and recovery systems. The spacecraft's equipment will generally duplicate that to be carried by Spacecraft 3, designated for the first manned Gemini flight. Spacecraft 3 was the subject of a development engineering inspection held at the McDonnell plant in June. Purpose of the inspection was to assure crew safety and the ability of the spacecraft and its systems to achieve its planned mission objectives. The GT3 launch is tentatively scheduled for mid-December. Following their selection, the GT3 crews began intensive flight preparation, including simulated flight training in the Gemini mission simulator at the McDonnell plant. The simulator's computers are programmed with launch, orbit, and re-entry information from which realistic mission modes are constructed. Failures can be programmed into the computers or inserted manually to test astronaut judgments and reactions. Engineering events during the reporting period included a heat test of the Gemini adapter cooling system. To determine that the cooling system would dissipate heat generated during launch, McDonnell engineers subjected the adapter and cooling system structures to heat of over 500 degrees Fahrenheit. Stresses were maintained by holding the system under elevated coolant pressure loads. The system successfully dissipated the heat. At the Elkton, Maryland facility of the Thiokol Chemical Corporation, the Gemini retrograde rocket motor was statically test-fired. The motor was also checked to determine its ability to withstand anticipated launch and flight vibrations. It met specifications on all counts. At Edwards Air Force Base, California, development progress on the North American paraglider recovery system was reflected in deployment tests using a full-scale Gemini test vehicle. Typical performance was exhibited in test number 7, conducted in late May. A time-controlled release mechanism freed the collapsed paraglider. The structure remained attached to the vehicle for 22 seconds to reduce opening shock. It was then allowed to fully distend. While problems in extraction and inflation have been overcome, difficulties still exist in the structure's tendency to go into a flat spin. Corrective measures are being investigated. At Martin, Baltimore, systems verification tests were completed on Gemini Launch Vehicle number 2. The vehicle is the second of 15 modified Air Force Titan II vehicles to be procured for the Gemini program. It was airlifted to Cape Kennedy in late June. By the end of the reporting period, Launch Vehicle number 3 had begun pre-launch and pre-orbital test programs in the vertical test facility. Launch Vehicle number 4 was undergoing airborne systems installation and checkout in the horizontal assembly area. Significant progress was recorded in the Agena program. At the Lockheed Missiles and Space Company, Sunnyvale, California, the aft rack assembly for the first Gemini Agena vehicle was delivered. The Gemini target vehicle is a basic Air Force Agena D, which will be modified with docking hardware, additional engine restart capability, a secondary propulsion system, and specialized communication systems. The first completed vehicle was accepted by the Air Force on April 1st. The first 6 months of 1964 recorded rapid progress in all areas of the Apollo program. At the White Sands Missile Range, preparations were underway for a test of the Apollo Launch Escape System. The system was required to propel the unmanned Boilerplate 12 command module away from the launch vehicle under conditions of high dynamic pressure in the transonic speed range. On May 13th, a powerful Little Joe 2 launch vehicle carried the payload to abort conditions. Special photographic techniques recorded the test. At 21,000 feet, a signal from the ground detonated the vehicle's thrust termination system. The explosion triggered the boilerplate's abort mechanism, igniting the launch escape motor and speeding the command module into its planned trajectory. "40 seconds after the abort signal was given, the launch escape system was jettisoned. A drogue chute helped stabilize the module. However, when the drogue chute was released, unexpected oscillations forced the main parachute risers over a sharp edge of the upper deck superstructure, causing one of the risers to sever. A canopy gore in one of the remaining chutes was torn by the escaping parachute shroud lines. The damaged chute remained inflated and helped land the command module within impact tolerances safe for man. All launch escape and Earth landing system sequences had performed perfectly. Command module oscillations will be dampened on future tests. During the early spring months, preparations at Cape Kennedy were underway for the first orbital launch of Apollo hardware. The test payload included Apollo Boilerplate Command Module 13, a dummy service module, and an adapter ring. Primary missions of the flight were to demonstrate the compatibility of the Saturn I launch vehicle and the Apollo spacecraft, and to test propulsion, structure, and flight control systems. No recovery was planned for the spacecraft. Launch occurred on May 28th. Despite the unscheduled shutdown of a first stage engine 21 seconds before planned first stage cutoff, the Saturn's guidance system successfully helped steer the second stage of the Saturn vehicle and the attached Apollo boilerplate into the programmed orbit. Onboard cameras recorded stage separation. All mission objectives were satisfied. The configuration of the Apollo airframe modules came a step closer to finalization as a result of a design engineering inspection held in April. The inspection was conducted at the Downey, California plant of North American Aviation. Human factor requirements and systems arrangements were of primary concern. Requested changes will be incorporated into the mock-ups for a second inspection to be held later in the year. In the manufacturing areas at Downey, work progressed on airframes number 6 and 9. The bonding of honeycomb and facing sheets was completed on airframe number 6. Airframe number 9, which is designated for the first Saturn 1B launch, had structural honeycomb segments applied to the forward crew compartment. The structure was placed in an autoclave for curing of the bonding agents. In June, transfer tests in the North American crew tunnel mock-up were performed under simulated weightless conditions. The tests were designed to uncover problems in removing the hatches and docking devices. A means of providing storage for the removed hardware is under study. The first Pratt & Whitney fuel cell for the Apollo program was received at Downey in January. During subsequent endurance runs, the cell performed a series of restart tests, exceeding its expected operating life by 15 hours. Propellant fuel and oxidizer tanks for the Apollo service module propulsion engine were in production at the Allison Division of General Motors, Indianapolis, Indiana. Qualification fuel tanks were pressurized to failure to determine their burst strength. Fuel tanks must be capable of withstanding 360 pounds per square inch pressure. The first qualifying test model of the service propulsion engine was completed at Aerojet General in January. The engine underwent its first development tests at the company's Sacramento facility and in a high-altitude chamber at the Arnold Engineering and Development Center, Tullahoma, Tennessee. The engine developed higher nozzle temperatures than were expected. The Columbium titanium nozzle extension is being redesigned to withstand temperatures of 2,000 degrees Fahrenheit. Facilities for testing the service propulsion engine were completed at the Manned Spacecraft Center's Propulsion Systems Development Facility, located at the White Sands Missile Range. Test engines will be checked out and mated to other service module components in the 2 static test stands. At Daytona, Florida, the first of 10 ACE, or Acceptance Checkout Equipment units, were in final assembly and test by General Electric. The first multiple unit computer program test complex will be delivered to North American's Downey plant in August. In late March, the first mock-up review of the 22-foot high lunar excursion module was held at the Grumman plant, Bethpage, Long Island. Purpose of the review was to establish a design freeze for a second mock-up review scheduled later in the year. Studies of access, mobility, and visibility were conducted with a space-suited subject performing functional tasks. The mock-up will be periodically updated to reflect technological advances and refinements in mission concept. One of the major development hurdles in the LEM program is that of perfecting a hypergolic lunar descent engine that can be throttled. One design is being perfected by Space Technology Labs, which began engine tests at their San Juan Capistrano facility. At Merritt Island, Florida, construction continued on the facilities that will be used in final pre-launch preparation for all future United States manned spacecraft. The Manned Spacecraft Center's operations and checkout building was 95% complete and was scheduled for occupancy in September. The building contains work areas for the assembly and checkout of manned spacecraft. Office space and facilities for crew training and flight preparation will also be provided. The weight and balance building was complete except for interior finishing. The remaining facilities, including the hypergolic test building, cryogenic test building, and environmental control systems building, were in varying stages of completion. At nearby Cape Kennedy, the arrival of Boilerplate 15 forecasted events in the Apollo launch program. The Boilerplate spacecraft will form the payload of the next Saturn launch, which is scheduled for late summer. The Boilerplate's configuration and flight plan are identical to those of Boilerplate 13. However, additional instrumentation will be carried, and a method of jettisoning the launch escape tower will be tested using the pitch control and launch escape motors. Preparations for the forthcoming Apollo test concluded a period of increased activity in manned spacecraft programs. The first 6 months of 1964 saw the new MSC facilities opened at Clear Lake. Research and development programs undertaken at Houston and at government and contractor facilities laid a solid foundation for future spaceflight activity. Fabrication of hardware for the Gemini and Apollo programs moved ahead rapidly. Launch vehicles and spacecraft for the Gemini and Apollo programs scored notable flight successes. And progress in the LEM program foreshadowed a period of increased testing activity. As this highly productive period drew to a close, progress in manned spacecraft center programs gave indication of equally successful activity in the months to come.